So for students in the back, can you hear me? Yeah, okay, great. So anytime you cannot hear, raise your hand. So I got some question about the homework. The second problem, there's a something like this. And so whenever, probably we didn't put it very clear in the picture, I screenshot from textbook. So whenever you see this thing, it basically means that the whole edge is clamped to the wall. And when it's clamped, it means that all degree freedom are fixed. Make sense or not? Yeah. Otherwise, you cannot really solve the problem, because it's. I think I emphasized in the first section when I talk about the bar element. If there's no boundary, you just imagine if there's nothing here. It's same for bar, same for beam, same for every element in our FEA. Mathematically, the K matrix is singular, determinant is 0. From our physical understanding is that there's no boundary condition and there's rigid body motion. So when you apply the force, it has rigid body motion. When you put in abacus, the whole structure will fly away. So there must have some boundary condition to solve the problem. So this is the homework, and boundary condition is that this whole edge is clamped to the wall. Any other question? Sorry. Resulting force where? Reaction force. Yes. Yes, absolutely. There will be reaction force. That's a good question. I can make the problem more complicated by asking about what the reaction force. But I think that problem I didn't really ask about what the reaction force. Right. But of course, I can always make the problem more complicated. Let's say I already solve everything, and then what is the reaction force applied by the wall to the structure? I think there was a question. Yeah.
Post the formula sheet like last time?
Yes. I will try to do it tomorrow. Yeah, you're welcome. Any other question? Okay. So in the last class, we talked about the derivation for the stiffness matrix. So basically, we have the strain energy of the CST element, and based on derivation, we have separate this part, and this part becomes our stiffness matrix for CST element. And CST element, since we have 3 nodes, and each node has 2 degree freedom displaced in X, displaced in Y, so the whole entire element has 6 degree freedom. Or mathematically can consider in this way. This is 3 by 6, so transpose 6 by 3. 6 by 3, 3 by 3, 3 by 6. So it should be 6 by 6 matrix. This is the volume, which is the constant of the CST element. So this is for the stiff matrix for CST element. So it depends on Young's modulus Poisson ratio. It depends on the coordinates of the 3 node. It depends on, of course, the area depends on the coordinate of 3 node. It depends on the thickness of our triangular element. And this is K. And for solving the unknown degree freedom KQ equal to F, we also need to know for the force supply, how do we put the force in the vector on the right hand of the equation. So the similar situation is that if we have the concentrated force applied at 3 nodes, and of course, I can apply this force in the random direction, and I can always resolve into the X component and the Y component, and X component, Y component, right? So for 3 nodes, node 1, XY component, node 2, XY component, node 3, XY component, and this becomes our F vector. And we already have the K. We have the F vector. We can solve for the Q, all degree freedom. And the next situation is, what if we have uniform distributed force applied on edge? And of course, in our undergrad class, I don't want to go too crazy. We can obviously that we have I give you a function f over x, or f as a function of x and y as randomly distributed force. But in our class, let's focus on similar situation. What if there's a uniform distributed force over the edge? Then again, I can resolve into the x component and y component And this distributed force over the edge is the force applied on the edge area. There's a thickness here, there's length in this dimension, so there's a small area. This is the force applied on this small area. So it becomes force per unit area. And we assume the edge length equal to edge length is L and the thickness is H. So mathematically, we do need to do integration of shape function times P as a function of x, y, and integration along the edge. This is the same as in the bin element. When we find the equivalent nodal force, we need to integrate shape function times distributed force and dx. So for more complicated situation, of course, we need to do that. But for this one, we can purely from our understanding, if there's a uniform distributed force on this edge, there's no reason that node 1 get a higher equivalent nodal force than node 2 or otherwise. So we can simply understand since it's uniform distributed, so what we can do is that calculate total force in the x direction, which is force per unit area times this area. And we divide by half on the, since it's the example here is edge 1, 2, so half here. And similarly, the total force applied in the y direction, split half to node 1 and 2. And we're done. So, and of course, if it's the edge, if the force applied on the edge on this edge, then simply these two components become 0. And half here, right? Same thing. The third one is body force. Body force we can consider as is uniform distributed force over the volume. So it could be, in real life example, could be gravity, could be magnetic force, just different direction. It doesn't matter. So since it's uniform distributed force over the volume, the unit we put as force per unit volume. And let's assume that the area of the triangular element is A and the thickness H. Same thing. You can use, we already derived shape function n1, n2, n3. So you can integrate n1 times distributed force and do the integration. And if you use n1, it becomes nodal force at node 1. You use n2 for integration, become nodal force at node 2. Same thing for node 3, integrate n3. But again, since it's the body force here, we are talking about the uniform distributed force. No matter it's the gravity or magnetic force, it should be uniformly distributed over the volume. And again, based on our understanding scheme or derivation part, you can check the textbook for the derivation, the integration part for this one and the integration part for this one. But based on the understanding, since you uniform distribute over the volume, there's no reason one node get a higher equivalent nodal force than the other two nodes. So again, the total force in the x direction, force per unit volume times A times H, which is the volume of the CST element, and split to 3 nodes in the x direction, divided by 3. And similarly, we can, this is total force in the y direction, and we have y component divided by 3. So this is the how to find the k, how to find the f vector. And of course, you calculate inverse of k times the f vector, you get the nodal degree freedom.
So if you're given like one like gravity body force, is it the same for like dx, dy for all of them basically? Like over to
No. No. Let's say if that's a good question. So we normally assume this is x coordinate, this is y coordinate, and let's say you have random triangular element, and normally we would consider gravity is in the y direction, right? So in this situation, we can consider the body force in the x direction equal to 0. And yeah, this is if this is the positive y, then this is negative y direction. So yeah, so basically 0, 0, 0, and the total weight divided by 3, and then you have negative sign. Make sense or not? Okay. Any other question? Thank you for the question. Okay. If no question, we can do an example problem. The content today will be included in exam 2. Up until today, yes. And Friday will be exam review class. Let's say we have a square element. Bottom edge surface clamped the surface to the ground, and on the top surface, it has roller support. And of course, since we already learned a CST element, we are modeling this structure using two CST elements, two triangular elements. Dimension, the edge length of a square element is square structure. I cannot say square element. We are using CST element. The square structure, 1 meter, 1 meter. We have distributed force applied on top edge. It's applied on top surface. So let's imagine you have this square element and it's on this top surface. So I can only draw it here, but you need to know it's applied on top surface. So this F is distributed force. F equal to kilonewton per meter square on top edge. Material property, Young's modulus. Poisson ratio, 0.25. Thickness of the element. Calculate stress in our structure. So this is like more closer to a real life problem. We know what material we want to use for our structure, for this square structure. Young's modulus Poisson ratio is given. So we know the material property. Dimension of the structure is given. This square edge length is 1, thickness is 0.1. Force is given, applied on top edge. This is the force. Boundary condition given. Bottom edge surface is clamped to the ground, and top surface is roller support. So material property, geometry, loading condition, boundary condition, calculate stress. It's a typical structure problem. And now since we learned everything about CST element, we should be able to solve this kind of problem. So we know interpolation. We talked about in the first lecture, we talked about interpolation, and then we talked about the K matrix, then we talked about how to put the F into the KQ to F. So now we can combine everything together and solve this problem. Where should we start? How to calculate stress in our structure. Yes. Yes, we do need to solve two sets of B and C for two CST elements. Yes. And what is after that? What is after that? After solving the F and B and C. Yeah. Yes. And then calculate the strain and then calculate stress. Yeah, but yes, you're correct. But that's part of our problem. But you need to know that strain equal to B matrix times Q. stress equal to C matrix times strain vector. The problem is that where's the Q? Right? You mentioned we need to calculate F and B and C. But where's the Q vector? How to calculate Q vector? K matrix, yes. How to do that? Well, K matrix itself cannot solve K for each element, or what should we do? Anyone? So now the question is how to solve the Q.
We apply if the uniform distribution along an edge, we have our edge length and we have our thickness.
Yes.
We can from there start determining the forces in each direction.
Yes.
At each node.
Yes, that is F vector we're talking about, right?
Yeah.
So how to solve our unknown degree of freedom? Well, let's first ask how many unknown degree of freedom here in our structure? How many? 2. Any other opinion? What? 1. Any other opinion? Who said 2? Which 2?
So you go to the top 2 nodes.
Why is 1? Which one?
Basically, due to the roller, it's only capable of motion in one direction. Thus, only has 1 degree of freedom.
But we have 2 nodes.
Two nodes that are at a fixed distance.
But still there are 2 nodes. Well, you cannot really say they are fixed distance because all our structure in our undergrad solid mechanics, they're deformable structures. They're not rigid body, right? The deformation may not be like super large, but since it's, let's say you have metal, you have force applied, there should be, since we're calculating strain stress, there are displacement, relative displacement between these 2 nodes. Okay, yeah, should be 2. So first, let's make it clear. Let's mark it as node 1, 2, 3, 4. 2, 3, 4. So before we apply boundary condition, our system should have total 8 degree freedom. Are you guys agreeing with me or not? 8 degree freedom. So we have 4 nodes. Each node has displacement x, displacement y. So we have 8 degree freedom. And after apply boundary condition, everything related to node 1 and node 2, they're gone because they're clamped to the bottom surface. For node 3 and node 4, since this is rotor support, it cannot move in the y direction. It can only move in the x direction. So node 3 has 1 degree freedom, node 4 has 1 degree freedom. So in the end, after apply boundary condition, it should be 2 by 2. So this type of question I can ask during the exam. I said after apply boundary condition, it should not be exceeding 2 by 2 for easy for you to calculate. So okay, now we know that we have 2 unknown degree freedom. How to solve these 2 unknown degree freedom? How to solve U3 and U4? Stiffy matrix for which one? Stiffy matrix for this element, for this element, for what? 1, 3, 4. So let's say what do you mean is that we have okay, let's say let's put which one? 1, 2. Let's put this one as element 1, this as element 2. So K equal to 2. Is this what you mean? Set the K for the second element times Q equal to F. And we solve for U3, U4. Is this correct or not? This is a very important question. Is this correct or not? Because I saw very frequently that this kind of common mistake in previous semesters.
Well, you have to define the force or the force vector the way that you showed us, where it's the uniformly distributed force with some length, the thickness over here.
Yes, that is the force vector. Yes, you are correct. So is this one correct for solving the U3, U4? So we find the K stiffness for the second element, and this is on these two edge, we can have the vector, force vector based on the uniform distributed force on this edge, and we solve for U3, U4. Is this correct or not? Who said no? Why?
Very much just, I feel like there's, with the existence of element one, that's going to interfere in some way. And that, if you solve it that way, it's not gonna work. I can't really explain it.
Yes, thank you. So we always, no matter how we describe our structure using FEA method, we always need to understand this is a system. This is one structure. We just using FEA method to describe in the way that, okay, this become one element and this become one element. But let's say before you learn the FEA, you know that this is one structure, right? This is, if you consider this one structure and you have force applied here, have boundary condition applied here, and rotor support applied here, once you consider this whole structure, or you consider this is only this part, is completely different thing. The result will be completely different. And this is same as some students ask me about the homework. It's very similar. A very common mistake in FEA. Maybe there's some distributed force applied here or some other things apply. And I think the question in the homework I asked like the bending moment shear force at node 3. So for solving the unknown degree of freedom, it's not just you have for the second element and you have the F for second element, and you put in the second element calculate to F, and you solve the unknown degree of freedom, and then you calculate bending moment shear force here. No. This entire part is one bin. We just separate into two elements. And when you have this part, it definitely different than what do you think, okay, I only consider this part and put it KQ to F. KQ equal to F is for the whole system. It's not for a single element. You can solve unknown degree of freedom. So for this homework, you always need to have K for this one, K for this one, assembly, and then apply boundary condition, and then solve unknown degree of freedom, and then you can go back to this element, solve for the bending moment shear force. Solving unknown degree of freedom, you always need to consider the whole system, not single element. Now back to our example problem. This KQ equal to F, when I asked about the U3, U4, of course, you can say that, okay, element 2 has 3 and 4, but this one absolutely affect if you consider just this triangular part or this entire square part. So if you only consider K for element 2, and then Q, and then F, it's wrong. What you need to do is that you have the K for this one, you have K for this one, you assemble them, become a big matrix 8 by 8, apply boundary condition, become 2 by 2, and then solve for U3, U4. That is correct way. When we use KQ equal to L to solve for unknown degree of freedom, always consider the whole system. The whole system. It's not a single element. So let's make it clear stepwise. Since this is more complicated question, let's make each step clear. The question asked about stress. So students already answered that equal to C matrix times strain. And the strain we already talked about in previous lecture, equal to the B matrix times unknown degree of freedom. And this unknown degree of freedom, sorry, this is complete entire degree of freedom, but unknown degree of freedom we need to solve using the K, Q equal to F for our entire system. And for the K, it's not just for any single element, it composes both of them. So we need to figure out K for element 1, K for element 2. And then, of course, we derived in last class for the K, it has thickness, area, B for element 1, transpose. How to write this one? Let's put the screen inside. Transpose, C matrix, B. And of course, you need to do the same thing for element 2. So stepwise, for each element, we need to calculate all the B's and C's for both elements based on the coordinates. And we need to have the B matrix and C matrix. Calculate the K matrix for each element and do assembly and solve unknown degree of freedom. And once we have unknown degree of freedom, we put all the degree of freedom in this equation. We can solve for strain. Six, 7. So this is stepwise how we calculate stress. So I think for complicated type of question like this, basically combined all the topics we learned in the CST. I would highly suggest, it's not required for your homework or your exam, but I highly recommend you guys to do this before you actually start calculating, because what I saw in the exam, in the homework I assume that you have a lot of time. So in the end, you can always figure out. Sometimes some students spend like several hours and then ask me during the office hour and figure out. But in the exam, it's very important that you don't do any work that does not stop in contributing to your final answer. So if you have something like this, let's say the question asks about stress. Okay, we need a strain. For strain, we need to have degree of freedom. How to calculate degree of freedom, K cubed to F, and how to find the K assembly. If you have very clear logic like this, then you know that, okay, first step, second step, third step, and you're not wasting your energy. So what I saw for the previous students in the exam is that they check all the equations provided and check problem statement and try to figure out which equation can fit into that problem and try everything they could, and they could not get a final answer because you don't have your own logical thinking and critical thinking like, if I want to calculate stress, what should I do? Then it's not like try to put every equation from what I provided and try to see which one fit and then calculate things that maybe not necessary and maybe you don't know where you are going. You just try to plug number into the equation and see if you could get some answer. So I would highly suggest that you can train yourself, do something like this for complicated question. So let's start from the K matrix. To make it very clear, element 1, I define as from node 1 to 2. Sorry. Let's define, doesn't matter. But because things I calculate is based on this is element 1, this is element 2, but it doesn't matter. You can do it any way you want. So for element 1, as I said, the node order, the first node doesn't matter. You can use this as first node. You can use node 3 as first node or node 4 as first node, but it has to be counterclockwise if you want to use the equation we derived in this class. So let's define the 1, 3, and 4. So in this situation, x1, y1, and the second node is node 3. Don't write x3, y3 because in that way you can never calculate B and C. The x1, y1, x2, y2, x3, y3 represent the first node, second node, and the third node. This is the second node. This is third node. Don't get confused. So x2, y2, x3, y3. And for element 2, again, first node can start from anywhere, and it has to be counterclockwise. So let's make just 1 to 2 to 3. Less confusing to you guys. So we have x1, y1, x2, y2 equal to 0. x3, y3 equal to 1. Now with all the coordinates, we can calculate all the B and C for each element. So for the first element, B1, if you want to know the original equation, check your previous lecture note. I'm not going to repeat that part here. B2, C2. Yeah.
How to calculate your F's and B's and C's, is that going to be on the formula sheet?
Yes, I will provide it. I don't expect you guys to memorize that. B2, C2, B3, C3. If you guys confused about like what is the original equation, I can show you here very quickly. You can check your lecture notes. These are the F and B and C. It based on the coordinates. Since I already wrote all the coordinates, B and C can be calculated very easily. So these are the F, these are the B and C for our two elements. And then we can write, second step, we can write the B matrix for each element. For element 1, we have, again, check your lecture note. The definition of the B matrix 0, 0, 1, 0, negative 1, 0. For the second element, we have -1, 0. One. Again, show you very quickly our B matrix definition. Sorry, I need to scroll back and forth. I know some of you really hate that. So this is our derivation part for the B matrix. Our 1/2A here equal to 1. This is 1. And you put all the B and C calculated, become the B matrix. That's how we got the B matrix for element 1, B matrix for element 2. And we know the K matrix, it has B transpose times C times B. So for the C matrix, it purely depends on the Young's modulus to Poisson ratio. So let's plug in those two values in our C matrix. So for the C matrix, we don't need to really differentiate like element 1, element 2 because it's the same, right? As long as element 1 and 2 using the same material, the C matrix should be the same. One 0.25. One minus 0.25. So this is C matrix.
This time you go 1/2A, but that includes one in this space.
1/2A is included. I didn't ignore anything. What's the area of this one? 1/2. 1/2A. A is 1/2. 1/2A equal to 1.
Yeah.
Why the whole thing is wrong? Which part is wrong?
In a different problem where 1/2A can for 1, you would multiply B matrix. Okay, that's all.
Yeah. So I can one over two 2A. Yeah. Any other question? So again, if you want to go to standard way, B transpose times C times B, it becomes 6x6 matrix. And we have two 6x6 matrix. After assembly, we have 8x8 matrix. I don't think we should waste our life for writing those complete matrix. I do not believe we should do that. So since we only have two unknown degree freedom, for the first element, we only need 4 components, right? Everything related to U3 and U4. And for the second element, we only need 1 component. Make sense or not? So for the first element, we only need U3, U4, the corresponding component. So it should be 2 by 2, 4 components. For the second element, we only need U3, 1 component. So do not write a complete matrix. It's just a waste of your life. So for the element, of course, you need to use MATLAB. I don't expect you guys to calculate by hand. HA B1 transpose C B1. So I only write 4 components. that's related to U3, U4. Let's put the row index here, U1, V1, U3, V3, U4, V4. So we have this is the first element. And for the second element, we only need one component. Again, I write the row index here, U1, V1, U2, V2, U3, V3. And we only need the component that corresponding to U3, one component. And after assembly, it becomes 2 by 2. U3, U4. And what should we put in the force vector? It should correspond to F3x, F4x, right? What is F3x? What is F4x? Anyone? We have force per unit area. We have this dimension and this dimension, which is the area, the force applied. And it's uniform distributed. We talked about that there's no reason one node to get a higher equivalent force than the other one. So we calculate the force, which is 100 kilonewton per meter square times 1 meter times 0.1 meter. This is total force, and half and node 2 and node 3. Make sense or not?
Yes.
Okay. Thank you. Thickness, edge length, half. And the same thing for node 4. (100 kilonewton), thickness, edge length, half. We solve U3, U4, Any question?
And 1/2A included in the B matrix,
Yes, I already answered right.
so 1/2A is the B matrix.
Yes,
Oh.
yes. A equal to 1/2, 1/2A equal to 1. Any other question? What the equation for what? Oh, so this is a uniform distributed force over the edge area, 100 kilonewton per meter square. And our edge area You have the edge length equal to 1 meter, the thickness 0.1. So this area equal to 1 times thickness 0.1. That's why we have area and half to 2 nodes. If you want to know the original equation, it's yeah. So the thickness, edge length. Yeah. Any other question? What time is it now? We have 1 minute. One strain. Then I will let you guys go. The strain for element 1. Equal to B times the Q. So we have the B. And for the Q, the complete degree freedom for this element, for element 1, U3, V3 equal to 0, U4, V4. And it's equal to 0, 0, 2.5. Shear strain, non-zero. Normal strain X, Y, they are 0. Any question?
Please note it, E, X, X, and Y, Y, what's that symbol on here?
Strain X direction, strain Y direction, and shear strain.
Okay.
Yeah. Thank you for coming and have a great day.